Hello all, let us discuss about the mechanical work or pressure volume work of a particular system. For that we have to consider a particular system. Here I am going to consider a cylinder which is connected with a piston, and this cylinder is filled with a gas having volume V volume and internal pressure Pi, and the area of cross section of this particular cylinder is A. Now we are going to do some work in this system. Either it can be on the system or by the system. If you are doing any work on the system, work done will be, the sign of work done will be positive, and if the work is done by the system, the sign of work done will be negative. So consider that the external pressure is P. So if the external pressure P is greater than the internal pressure Pi, external pressure P is greater than internal pressure Pi, then it is work done on the system, or we can say it as compression. Or if the external pressure P is less than internal pressure Pi, then the work done is by the system, or we can say it is expansion. Here the process occur is expansion of the gas inside the cylinder. So here we are going to consider a work done by the system or the expansion of the gas, that is P is less than Pi. Here the area of cross section of the cylinder is A, and here the process occurs expansion. So consider the initial volume is here, initial volume is this, and when the expansion of gas occurs, the piston moves dl distance from the initial volume, and it is the distance from here to here. Here this is V1, and this V1 is expanded to V2 by a small distance dl. So if we consider the volume change, during the expansion, we can write it as A into dl. A is the area of cross section and dl is the distance, change in distance. If we find out the force on this piston, the force on this piston F equal to pressure into the area of the cross section. Area of cross section. That is F equal to P into A. And the work done on this piston, W equal to force into distance traveled by this piston. That is W equal to F into dl. That is, we can substitute the value of force P equal to A here. So we'll get an equation like this. W equal to E into A into dl. Here A into dl is volume change. That means W equal to P dV. Since the work done by the system, that is the sign conversion is negative, so here W is minus P dV. So work done by the system or the work done when expansion occurs equal to minus P dV. When we find out the finite volume change from V1 to V2, we can write W work done W equal to integral minus P dV. And here we are going to consider the change from V1 to V2. So integral V1 to V2 minus P dV. That is minus P into V2 minus V1, that is minus P delta V. This is the finite done when expansion occurs from V1 to V2. Same way we can find out the work done during compression of the gas also. If compression of the gas occurs, then work done W equal to minus P into V1 minus V2. Here this is, and here this will be a negative quantity, so this will be P into negative delta V. Finally, we'll get work done W equal to positive P delta V. If expansion occurs, then minus P delta V is the work done. If compression of gas occurs, then work done will be P delta V. Now we are going to introduce a new term which is enthalpy. Here we are going to consider a system in which the pressure is constant. There is no pressure change. And consider the volume of the system is V1. It is the initial volume, and from this initial volume the system is converted to a final volume V2. But imagine that there is no pressure change. That is, we are doing this process at constant pressure. So here work done will be initial volume work done, that is W equal to minus P delta V. Minus P delta V. So according to first law of thermodynamics, delta E equal to Q plus delta W. Here we can write Q as Qp since the system is at constant pressure, and W is as P delta V. That is delta E equal to Qp minus P delta V. Here I am going to rewrite delta E as E2 minus E1. It is energy, the final energy as E2 and initial energy as E1, and Qp P into V2. Delta V is rewritten as V2 minus V1. That is E2 minus E1 equal to Qp minus PV2 plus PV1. So now I am going to bring this term here, these two terms left side. The equation becomes E2 plus PV2 minus E1 minus PV1 equal to QP. Or I can write this as E2 plus PV2 minus of E1 plus PV1 equal to QP. The term E plus PV is known as enthalpy. Here E plus PV is enthalpy. Enthalpy is represented by using the letter H, and these two terms are, this is H2 and this is H1. H equal to E plus PV. That is, enthalpy is the sum of internal energy and the product of pressure and work. Or we can define it as, it is the total energy of a system. It is the total energy stored in a system. It is the total energy stored in a system. And it is a state function. It is a state function and an extensive property. So, enthalpy is the total energy stored in a system, and it is the sum of the total energy and the product of pressure and volume, and it is a state function and extensive property. Now let us find out the enthalpy change of a system. Now we have H equal to E plus PV. Here we are going to find out the enthalpy change. So delta H equal to delta E plus delta P into V. So delta H equal to delta E plus P delta V plus V delta P. When the process is carried out at a constant pressure, when it carried out at a constant pressure, delta P, constant pressure, delta P equal to 0. So we can rewrite this equation as delta H equal to delta E plus P delta V. Equation number, consider this is as equation number 1. According to first law of thermodynamics, E equal to Q plus W. Here we are only considering the expansion. So work done equal to, W equal to minus P delta V. When we apply minus P delta V here, this delta E equal to Q minus P delta V. This is equation number 2. We can apply equation 2 in equation 1. When 2 in 1 implies, we'll get delta H equal to Q minus P delta V plus P delta V, and this P delta V and P delta V will be cancelled out. That is delta H equal to Q. Since the entire process is done at constant pressure, delta H equal to QP. That is, enthalpy change of a reaction is the heat evolved or absorbed at a constant pressure. So we can say enthalpy change is the heat evolved or heat evolved or absorbed at constant pressure and temperature. So let us find out the relation between delta H and delta E, that is change in enthalpy and a change in energy. So we can write delta H, change in enthalpy, as H2 minus H1. We know H2 is E2 plus PV, P2 V2, and H1 is E1 plus P1 V1. That if you are removing the bracket, we will get E2 plus P2 V2 minus E1 minus P1 V1. So I am going to rewrite it as, going to write the energies, two energies together, that is E2 minus E1, and the pressure volume terms together, that is plus P2 V2 minus P1 V1. This is the energy change, that is, this is delta E, and this is delta PV. This is the relation between enthalpy change and the energy change. Here, if we are expanding this term, we will get delta H equal to delta E plus P delta V plus V delta P. But when we are doing a process at constant pressure, this term equals to 0, that is delta H equal to delta E plus P delta V. This is the relation of enthalpy change and energy change at constant pressure. Then what about the relation of enthalpy change and energy change for a real gas? We know for real gas, PV equal to, real gas equation equal to PV equals nRT. So V equal to nRT divided by P, and we can write delta V as delta nRT divided by P. The delta is applicable only for N since R is gas constant, and we are considering this system at constant pressure and constant temperature, since these two terms are considered as constant. So delta N is the only change in term, and delta En is the number of moles of product, N is the number of moles of product minus number of moles of reactant. So for a real gas, delta H equal to delta E plus delta N RT divided by P. So delta H equal to delta E plus P delta V. If you are considering that the change in volume is negligible, then delta V becomes 0. That is, delta H becomes delta E. So we know delta H equal to QP and delta E equal to Q plus W. Delta, according to first law, delta E is equal to Q plus W, and when delta W equal to P delta V, And when delta V becomes 0, delta E equal to Q at a constant volume. So, here delta H equal to delta E. So, QP equal to QV. That is for an ideal gas, delta H equal to delta E plus delta nRT divided by P, and this QP equal to QV plus delta nRT divided by P. This is the equation for ideal gas at a constant pressure and a constant volume.